Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's begin chapter 8. Chapter 8 is going to take us in a different direction than some of the previous chapters because we've been focusing mostly throughout the year on linear growth. We've been talking about linear equations or linear functions that have a constant growth rate. And when you graph them, you see the graph is a straight line. Well, this chapter is going to show a different pattern of growth where we have nonlinear growth. And with nonlinear growth, there are a few different types of situations that would create nonlinear growth. But the one that we're going to be exploring in detail is going to be exponential growth and exponential growth functions. So just to clarify, linear growth occurs when a situation has a constant growth rate. You see that as a straight line on the graph. So we had like equations where you had a growth rate and a starting amount, right? The y-intercept and the slope of the line. Or in the situation, it's like you start off with $5 and you save $2 per week. How much money are you going to have after X number of weeks? This is a linear growth type of a situation. When we were working with proportions, when you had negative 5x could be a proportional type of equation, but the rate of growth in this case is not really growth, it's decline because it's going down 5 every time. So if you, every time you went to the, well, maybe that's not the best example because you wouldn't start with 0 and then go down. Let's say 5x. So it is increasing by 5. So let's start, say you start to say $5 a day or a week or a month, I don't know, let's say a day, where Y represents how much total amount of money you've saved over time, and X is the number of days or the weeks or the months or whatever the unit is that you are using for saving. Okay, so these are both linear type growth situations. So what is nonlinear growth? This occurs in a number of situations, but it's characterized by a situation that does not have a constant growth rate and a graph that is not straight. So an example of nonlinear growth would be like y equals x squared. So if x is equal to 1, y is equal to 1. If x is equal to 2, this becomes 4. If that's 3, that's 9. So it's not going up at a constant rate. It's changing every single time. So this has an exponent. So sometimes nonlinear growth is exponential growth, which we will see what these graphs look like in detail in this chapter. Another example of nonlinear growth would be like y over, hold on for a second, not k. Let's say y is, and then you say maybe 12 over x. So this particular kind of a graph is not a straight line. It does have a curved type of a line shape. So most of the time you're going to find linear growth, well, in fact, all the time, you're going to find linear growth always has your x, your independent variable, is raised to the first power. And you don't see the 1 there, but there's a ninja 1 there. You can't see it, but it is there. Same thing here. In this case, though, you get your exponential growth, so you have some exponent other than the number 1 that's being applied to your independent variable. And then the fact that you're dividing by your independent variable instead of taking a number and dividing from the independent variable, that makes this one nonlinear. All right, have you ever noticed that the sun rises earlier and sets later in the summer than it does in the winter? If you live north of the equator, you may have noticed that in December, you often wake up for school when it's still dark. However, if you wake up at the same time in May, the sun would be shining. The number of hours of sunlight in any one place changes during the year, unless you live directly at the equator, but even that, it kind of changes a little bit. This is because the Earth's tilt changes in comparison to the sun. For a little science lesson, there you go. The number of hours of daylight is approximately equal to the number of hours of darkness just 2 times out of the year, during the fall equinox and the spring equinox. So first day of spring, first day of fall, The day and the night are exactly the same. If you compare the average number of hours of daylight to the time of year on the graph, you would see a pattern in how the number of hours of daylight changes. Today, you're going to explore a couple of different situations in tables and graphs that change in different ways. You're going to build strategies for visualizing different patterns of growth. As you work, ask these types of questions or reflect on these types of questions. How does it grow? What happens when one measurement changes, and how can we see the pattern of growth in a table? All right, there was problem number one here, but it was a little bit complicated, takes a little bit of time, and so it's not really essential to this particular lesson. It was just basically a few different examples of linear and nonlinear growth, but we'll see enough of that popping up. You'll get the idea. Okay, so let's start with this situation. Now that you have predicted what different graphs would look like, we didn't. I just told you we skipped over that problem. You're going to investigate how some measures are related. To start, consider this situation. Okay. Oscar puts $1,000 of principal in a bank that earns 2% simple interest each month. He wants to track how his money is growing over time. Oscar is using the formula at the right to calculate how much interest he will earn on investments that are earning simple interest. He knows that simple interest is paid only on the original amount, which we call the principal. That's the amount of money, like $1,000, since that's what you're putting into the bank, we call that the principal. The amount of money that was invested for 2 months, he wrote this equation here. I is equal to 1,000 times 0.02 times 2, and that equals 40. Okay, so what do all these different parts mean? Hold on for 1 second. Okay, excuse me. Not that you noticed any time going back. Okay, so I equals PRT. That is the formula for simple interest, and I believe your M&Ms tonight for the homework, or for today, would have all of this spelled out for you. But it's a good idea to just write it down. The more you get written down here, the less you'd have to fill in for the M&Ms. So I refers to the interest that has been earned. How do you find out what that interest is? Well, you multiply the amount of your principal, right? Remember, you always have to start with some starting amount. In this case, it's the principal, we call it, and you deposit that in the account, and it makes 2% simple interest. So the interest rate is going to be the R. Why didn't they put something for T there? That's really weird. So this is the decimal equivalent of 2%, and then for 2 months, since you're earning the interest each month, that's going to be the time. So P is principal, R is the interest rate, which starts off as a percent that you change to a decimal number, and the T is your time period. It could be months, weeks, days, years, could be anything. Usually it's either years or months. Sometimes it's weeks. When you're talking about credit card balances, it's by the day. So what we need to do whenever we solve these problems is we need to identify from the problem using the 5D process. We need to define all of our variables. And so that's what this would be right here. You would say, we're trying to find the interest earned, so that we're just going to leave it as the I. The principal we know. Let's define that as $1,000. The interest rate we know is 2%, which we can convert to a decimal number because we're going to want to use our calculators for this. And then the time is in months. In this case, they said 2 months. So I equals PRT. Let's go ahead and put that information in. Now, we've already told you what the interest is because we know what the time is. But I like to do it this way. I like to say, all right, let's keep this in the form of a proportional type of an equation where we know that $1,000 is the principal and the interest rate is 2%. If I figure out how much that is, what is 2% of 1,000? That is going to tell me how much money I'm going to make in interest every single month. Remember, T is equal to the number of months in this situation. So that's why we got $40 here. 2 months would be $20 for every month. 20 times 2 is 40. So once we've got that in place, the $20 per month, then we can actually declare the answer in this case is going to be interest earned, $20 per month for 2 months is $40 total in interest. Okay, so this is the process that I generally use. I define my variables, right? Your describe and your define portion of the 5D process right here. We're going to do the process by using the simple interest formula where we plug in the information and then you simplify until you've got your answer. Now, we generally start where we're trying to find interest earned, but there are going to be situations where they tell you the interest and the principal and the amount of time, and you've got to use algebraic reasoning to solve for R so you can declare what the interest rate was for that situation. Or maybe how much time did it take? Or maybe how much was the principal? How much was deposited or how much was borrowed? Okay. So if you print off resource page 8.1.1a, you will see a table and you will see a graph that is provided to help with this problem. So it says on this resource page, complete the table to show the interest Omar has earned after 1, 2, 3, 4, and 5 months. How do you find his new balance each particular month? Well, let's find out. Let's go ahead and get started on this part right now. So one thing we learned from doing that work in the previous page was the interest is going to be equal to $20 for every single month. So after 1 month, it should be $20, correct? After 2 months, it should be $40. After 3 months, it would be $60. After 4 months, it would be $80. And after 5 months, you would have earned $100 in interest, which, by the way, this never, ever, ever happens. Nobody makes money that easily, that quickly. I'm sorry. In a fantasy world, maybe this works, but not in the real world. You'd be appalled at how little a bank will pay you in interest in your savings account, but whatever, you'll find that out soon enough. All right, so the new bank balance. After 1 month, you deposited $1,000, right? So the new bank balance would be $1,020. After the second month, you earned $40. So you add that to 100. No, it's not 100, it's 1,000. You add that to the 1,000, that becomes 1,040. Then 1,060, then 1,080, and then 1,100. Okay? So if we are graphing, if I is the dependent variable and T is the independent variable, then this is a proportional type of a situation, right? So after no months, so we're going to focus on this column right here. This is the column that is going to get graphed because that's the column for interest earned. If we were going to graph for the bank balance, we would have to say that the new bank balance, actually, that wouldn't be that. I would say the total amount that we have in the bank would be equal to 20T plus 1,000, right? Because you started with a deposit of $1,000 and it grows by $20 per month. So that is not what the dependent variable is. It's not the balance. It is actually the interest earned. So we will not be using this formula for graphing. Okay, so let's go ahead and plot these as your ordered pairs. Remember, you got 0, 0, you got 1, 20, you've got 2, 40, you've got 3, 60, 4, 80, and 5, 100. So I'm going to go ahead. 0, 0 is located right there. After 1 month, you got $20. What is that? That looks horrible. I might need to replace this. This just looks a little sloppy. Actually, hold on for a second. My OCD is taking over. Hold up. Oh my gosh, that is so much better. I can breathe easier now. OCD is rough, people. Okay, so where are we? Where are we? Let's go ahead and close that. All right, so what were we doing again? Did I have a color preference here? We got your 0, 0 is right there. You got your 1, 20 is right here. And when I'm graphing, I like to graph, especially with the linear functions, I like to graph ones that are farthest away from each other. So 5, 100 is right around here. And so when I connect those dots with a straight line, no, yes, maybe, all right, that should include all of our points. So let's make sure that does. 240 should have been located there. Yes, it is. 360 should be located there. It is. And 480 is located right there. Okay. I think I might be able to adjust that just a little bit. That's much better. All right. So that is our graph. Once again, the dependent variable was the interest earned, and the independent variable was the amount of time, because that's what we're controlling. Okay. All right. What else do we have to do here? Says, what patterns do you notice in the table and the graph? How can you see each pattern in the other representations? Okay, so we do see a pattern of growth, right? This is increasing by 20 every single time, and so is this. That is a slope ratio of going up 20 for every one that you go to the right, right? So the slope ratio is equal to 20 over 1. So the pattern of growth, right? Growth rate, the amount of interest earned in this case is the slope of the line. I think that pretty much covers it, right? As far as patterns go. All right, so use the pattern you have found to predict how long it will take Oscar to have $1,800 in the bank. Oh, I didn't cover it up. Well, there's our answer. Ooh. Okay, well, let's go ahead and see how we would find that on the graph. So if he's, oh, we can't find it on the graph, can we? For him to have $1,800 would mean he would have to earn $800 in interest, because he started off with 1,000. So I guess that's where we begin, where it's like, okay, so I equals PRT, but the interest earned for this situation has to be 800 because, nope. Now let's do this. Now let's do this color. I like that color. Because 1,000, the amount deposited, needs to be subtracted from your total amount so that you will know how much money was earned, right? The interest is earned. So $800, that's what we have to put in place of the I. So we know that the principal was 1,000. We know the interest rate was 2%. In decimal form is 0.02. So what we need to do is figure out the time. Now remember, we could write this as 800 is equal to 20t, because we know that the principal times the interest rate gives you $20 per month. So now the last step, divide each side by 20, and you get 40. So that means t, which is the number of months, is 40. Now it says compare your graph and part. No, we didn't do that part, so we're just going to skip that. Okay, so this is how simple interest works. Simple interest is a situation that is linear growth. There's a constant growth rate, and depending on whether you are graphing the interest earned or the total balance, it is either a proportional relationship for the interest earned, or it is just a linear relationship when you have the bank balance as your dependent variable. Now, here's an entirely different situation. Anita bought a special baseball card for $8. Later, she decided to sell it, but she wanted to make a profit. So she added up 50% to the price she paid and sold the card to Brandon. He decided to sell it, and he also wanted to make a profit, so he jacked up the price 50% and sold it to Casey. Casey, same thing, increased the price by 50%, selling it to Eli, and then Eli did the exact same thing, raising the price 50% and sold it to Fernanda. So now this has a different resource page, so feel free to print off this one as well. Now hold on for a second. Is this one going to drive me? No, I guess it's not. I guess I'm going to graph it on this one right here. That one doesn't look too bad. So what we need to do now is we need to figure out, all right, how much is the price increase going to be every single time? Is it going to be a constant growth rate like we saw in the previous example? It's the 50% is constant every single time. Let's see what that does to the increase and the new price every single time. This is one where you'll probably want to have your calculator out. And this chapter, by the way, this is the chapter where we're going to end up using formulas where we're going to start using these buttons here. We're going to start using the scientific calculator the very first time. Up until right now, we've been able to get away just using a basic calculator because we've just been focusing on just the basic operations. But with exponential growth, we're going to have to start using some of these other buttons. Okay, so let's see what we've got here. I'm going to use my blue, and let's see. We start off with $8. So now, is this selling it for 50% markup? Nita bought a special baseball card, and she wants to mark it up 50%. Okay, let's go back to 7th grade for a second. We can either figure out what is 50% of $8, which we know is $4, right? And we can add that to the price. So the increase here is going to be $4, which means you're going to sell it. I'm going to go ahead and not write dollar signs in here if you're okay with that. Yes, let's be okay with that. So that means it's going to sell for $12, right? Because you add the increase to the original amount to get the new amount, which is $12. But we can also use this idea. If we just take 150% of $8, this incorporates the $8, the 100%, which is the $8, plus the additional 50% that got added on. So if I find out 150% of 8, I should get the $12 again. Let's do that on the calculator. Remember, 8 times 0.5 is the $4. That's just the amount of the markup. But if I want to find the new price, if I take 150% and write that in decimal form, that's 1.5, right? 100% is 1, 200% is 2, so 150% has to be between 1 and 2, it's 1.5. Multiply that times the 8, and that should give you the new amount. So you may recall that from last year, we spent a fair amount of time talking about the 2 different multipliers that could be used in this situation. If you're trying to find the amount of the markup, you use the 50%. If you want to find the new amount, use the 150%. Okay, so we're going to do probably, well, let's do, now we got to do both. Let's do both. Okay, so now you got $12, and now this dude who paid $12, who is it? Brandon paid $12 for the card. And now Brandon wants to sell it to Casey, and he's going to do the same thing. So what is 50% of 12? That would be $6, right? And when you add that to the 12, that means that he sold it for $18. If you took 150% of 12, you would get 18, guaranteed. Let's check it. 12 times 1.5 is 18. I told you. All right. Now, Casey wants to turn around and sell it, mark it up 50%. So Casey marks it up $9 and sells it for $27. Eli. And then Eli wants to do the same thing. Am I losing track of someone in there? I mean, how many times is this really being done? Let's just keep going. Half of 20, well, let's take, half of 27. 27 times 0.5 is 13.5. And then you add that on, that's going to be $40.50. I'm going to put that in there because we are talking about money. And then let's go ahead and take plus 27 just to verify that. Yes. And now let's take that and multiply it times 50%. So it's $20.25 for the last markup. And then when you add that to the $40.50, you get $60.75. This is what we refer to as exponential growth. because we're starting off with $8 and it goes up by 4, but then it goes up by 6, then it goes up by 9, then it goes up by 13.50. I should put the 0 in there. Then it goes up by 20.25, and it's going to continue growing by a little bit more every single time. So it's non-linear, this particular growth. So what does it say? How do you find the new price in each exchange? Well, each new price is 150% of the previous price. So let's go ahead and graph this. Notice that the new price, we are not graphing the increase in price. We're graphing the new price. So this is a situation where we have a starting amount, which was $8. And then after one exchange, we're going to focus on these guys right here, the new price. After one exchange, it's $12. Then for the next exchange, it's going to be 18, which puts us right around here. And in this situation, because it's non-linear, it's going to start curving up. We can't go through and cleanly point out here and connect the dots with a straight line. For me, this is actually kind of a challenge using this tool. It doesn't really, I mean, you'll see how frustrating it gets for me. For you with your pencil, hopefully you can draw a nice gradual curve for this. So the third exchange was 27. So let's go to where 27 would be somewhere around here, right? 24, 26, 27 is halfway in between there. For the next one, it's going to be about $40.50. So I'm just going to barely go over 40 right here. And then the next one, the fifth exchange, was $60.75. Whereas $60.75 is going to be close to $6, $61. So it's going to be somewhere in there. Okay, non-linear, right? Now, in this situation, I'm not sure if we actually need to connect the dots, because if you only, the price only goes up with each exchange, you wouldn't have half of an exchange. So I think this is supposed to stay discrete, just like that. So what patterns do you notice here? Well, the price increases by more with every transaction, correct? It's not going up at a constant rate. This is an example of exponential growth. So in the problems 2 and 3, one graph made a straight line, the other one was curved. How was the situation that created the straight line changing? Well, straight lines means it's changing at a rate that is constant, and in this case, it was $20 per month. Growth that creates a straight line shows constant change and is called linear growth. We talked about that. What made the graph in problem 8.3 curve? Well, it was exponential growth. The fact that it was increasing by 1% every single time based on the original amount, which was causing it to grow by more every single time because the new amount was growing. So just to kind of finish this up, oh, I guess we got another problem. This is a comparison. Stop it, get out of there. This is a comparison of the difference between linear growth at a constant rate for simple interest, let's call it 8% per year, where you start off with a certain amount of money and then it just grows at a constant rate, and exponential growth where it is compounded over time. And so we've been working with simple interest, but in chapter 8 we're going to focus almost entirely on compound interest that involves exponential growth. All banks, everything that we do in the financial world is based on compound interest. Nothing is simple interest except for our exercises in school, and maybe if grandma or grandpa teaches you a lesson and decides to pay you simple interest just to teach you how interest works, we will use simple interest. But it's not used by any banks or any credit cards or any financing anywhere. Okay, compound interest is the way things work. And you can see that banks would want, when they borrow or when they lend you money, would prefer to lend you money with compound interest because they're going to make more money over time. Look at the difference after 45 years that these two make. Okay, change this number, instead of being like 1, change it to 100,000. And you can imagine just how massive the interest is going to become over time. So exponential growth, nonlinear growth is a curved line. Constant rate growth is linear growth. That's a straight line. All right, Guillermo was studying the different, how much time do we have left? I better get cracking. Sorry. Guillermo was studying the two different situations below. He knows that one is represented by a line on the graph, the other is represented by a curve. So I'm going to go through this really, really quickly for you. Basketball tournament. Round one starts with 16 people. No, 16 teams. 8 of those teams win, 8 of them lose and are out of the tournament. So round two is the 8 winners. Half of those teams win, half lose. So round three has only 4 teams that won. And then round 4 is the championship where the winner gets the trophy. Okay, so that's one situation. Here's another situation, finishing homework. Problems left to complete. So you started with 16 problems in your homework. After 10 minutes, you've got 12 problems left. After 20 minutes, you got 8. After 30 minutes, you got 4. And I'm presuming after 40 minutes, you would have completed your homework. So this has a unit rate. 4 problems in every 10 minutes means that you're solving 1 problem every 2.5 minutes. So how do you see the changes taking place in each of these tables? What is going on there? Well, in the basketball tournament, each round is half the number of teams of the previous round. In the homework problem, the number of problems decreases by the same amount every 10 minutes. So one of these has a constant rate of change. The homework does. The tournament does not. So if you look at these two situations, you see which one is the homework problem and which one is the basketball tournament problem. Take a few seconds. Understanding the nature of a homework problem has constant growth, and the other is nonlinear growth. In this situation, it is exponential, but it's exponential decline, not exponential growth. Which one is which? Well, if you said that the straight line is the homework, that is correct. The straight line implies constant growth. This one must be the basketball tournament. The curve implies that a different number is taken away with each new round. So the number of teams that go home after each round is declining. And I'm wondering, I think this particular one, sorry, this is going a little bit long, but I really think that the number of teams remaining is going to be equal to, you started with 16. No, actually, I don't want to write that there. Hold on. Started with 16 teams, and it reduced by 1/2 every single time, right? Where x is going to be the exponent. So x, I guess that should be y, shouldn't it? Total number of teams is equal to started with 16, and then it goes down by 1/2 every single round. So I'm going to use my scientific calculator here. And I'm going to say 16. Oh, no, I can't do it with this one that way. I have to do it a slightly different way. I'm going to take 0.5 and raise that to the power of 4. And it gives me this as my decimal number. Now, that is when I put a 4 here. Let me move this over. That's me putting a 4 there, applying it to the rate of decline, and now I'm going to take that answer and multiply it times 16, and I bet I get 4 for an answer. Times 16, the answer is no. Okay, that's obviously wrong. Fourth one is 2. Oh, is the fifth one? Did I get this right? Is that 4, 2? Yeah, that's 2. All right, I'm going to have to think about that a little bit. I'm a little bit off. I know there's something that has to do with that. We'll just leave it as is. That's not really part of the lesson. So how much time did I go over? Quite a bit. I'm so sorry. Could have saved you a couple minutes with that last little bit of rambling. But that's it. Let's move on to the next activity. Take care. Bye.
Hey, feeling good, like I should. When in dark, I walk around the neighborhood.